So this first lecture, first official lecture on PH101, the last lecture was basically introduction to the course policy and things like that. The first lecture on 101 is going to be a run through on the couple of important developments that led to the construction of quantum mechanics as we know it. Okay, so in case you are not able to see or hear anything that I'm doing, please send me a message on the chat, and then I will be able to respond and let you know what's going on. So I request people not to write on the slides or do any annotation. So that is going to cause me a lot of problems. Okay. All right, so I have the other screen over here. So in case somebody wants to get in, I can always admit him or her. Okay, so I hope all of you can see the screen. So let us try and make this into a sort of a presentation mode. Okay, wait, no, that actually ruins it. All right. Okay, so as I told you, this first lecture is going to be a run through on some of the important developments that led to quantum mechanics. And on the first slide that you see, there are some historically very important figures who played a very important and central part in the construction of quantum mechanics. By the way, before I move on, Professor Vinod Chandra is there with me, and he has his email open. So in case you have any difficulty and you are not able to message me for some reason, just send him a quick email and we will sort it out. Okay, so there you have it. So there are some very important people whose work was central to understanding quantum mechanics. So your first homework in PH101 is to try to figure out what are these people and what are their names. Okay, so some of them might be obvious to you, like Einstein and Bohr and probably Dirac and Schrodinger to some of you. But try to figure out what the names of these people are. Okay, so you probably know all of them by name, but not face. So it will be an interesting exercise. So that's Planck, there is Heisenberg, there is Schrodinger. Okay, so let us start with what we already know. Okay, what do we already know? We know that up until about 1905 or 1900, physics was dominated by basically two very important lines of study. Okay, and this whole line of study comes under the collective banner of classical mechanics, which is what you have been exposed to up until this point in your education, except for some brief foray into quantum physics that you probably had in your high school. You have mostly been interested and studied what is called classical mechanics, and this is for a very important reason. The important reason is that the two pillars of classical mechanics, which are basically Newton's mechanics and Maxwell's electrodynamics, together help explain pretty much everything that we see around us. Okay, so whatever we see with our naked eye, there is a good chance that we might be able to explain that with using classical mechanics or electrodynamics. Okay, so the question really is, why do we have to go beyond that? Obviously, there are certain shortcomings of the foundations of classical mechanics that one hopes to address by going beyond classical mechanics, and that is the part that I hope to convey in this lecture, not in entirety, but in perhaps some amount of measure, because I want to be able to convey to you some of the important lines of thought, maybe experimental or maybe theoretical, that diverged from the classical mechanical prescription. Okay. So what are these two pillars of classical mechanics? The first, as you very well know, is Newton's laws, Newton's second law in particular. So from age immemorial, people have been trying to understand the very basic question of how do response and stimuli talk to each other. Right? Suppose if you disturb an object, how does it respond? Right? What is the response to an external stimulus? The external stimulus that Newton was interested in is called force, as you very well know. And Newton formulated a law of mechanics, Newton's second law of mechanics, that told you that whenever there is an external force on an object, the object accelerates. And the force and acceleration are directly proportional to each other. And the proportionality constant is called the mass of the object. Technically speaking, this is what is called the inertial mass of an object, which is not the same as the gravitational mass of an object that one measures in two gravitating objects. But let us ignore those subtleties. The force of an object, the force acting on the object, causes the object to accelerate. How much does it cause it to accelerate? It causes it to accelerate in proportion to the force, the proportionality constant being the mass. So for the same force, a lighter mass would accelerate much more than a heavier mass. There is one important aspect of this equation that we probably take for granted, and that is the notion of deterministic equations. What does that mean? This is, after all, a second order differential equations. The way we are taught, or if you've not been taught, the way you would be taught to solve this equation is you'd be given two constants of integration, maybe the initial position and initial velocity, and then you can simply integrate this equation twice and you can get the trajectory of the particle. The trajectory of the particle is basically the position vector of the particle as a function of time. So how does the particle move as you keep evolving in time? That is the fundamental question that we want to answer. This is a deterministic equation. A deterministic equation simply means the following. Suppose if I give you what the initial conditions are, where the particle was at time t equal to 0 and what the velocity of the particle is at time t equal to 0, I would be able to I would be able to determine very precisely what its future velocities and positions would be at all instants of time. The motion is deterministic. So I'm not going to say, well, there is a good chance that the particle can be found there, or there is a good chance the particle has a velocity of 10 meters per second. These are not statements one makes in classical mechanics, right? The statement one makes in classical mechanics is, given the initial position and given the initial velocity, this is exactly the future positions and velocities of the particle that you would see. So somebody raised their hand, so you can go ahead and type out the message as to what you want to say or ask if there is any question. So I request that you keep the questions at the end, but if I'm saying something that is very difficult to understand or there is any other technical complications, just type it in the message and I'll be able to understand what's going on. Okay. All right. So the second pillar of classical mechanics is Maxwell's electrodynamics. And this is basically what we studied during the first half of this course. And Maxwell's electrodynamics is a set of compact first order differential equations that tells you how the electric and magnetic fields evolve with respect to space and time. Okay. So there is 4 Maxwell's equations. How do I go to the messages? Okay, there's nobody here. Okay, so I don't see any messages up till now. If there is any messages, I will see them. Okay, so again, I request that people don't annotate on the slides. I'll try to see how I can prevent you from doing it as we go along. Anyway, so Maxwell's equations are basically 4 equations that so Ayush says that this is considering the mass of the body to be a constant. The complete equation would be F equals rate of change of momentum. That is a very good and very important point. So right now I'm neglecting relativistic effects. Okay, so relativity tells you that you cannot just treat the mass as a constant. It's the inertial mass, that's the rest mass, that is a constant. But for now, I'm treating Newton's laws as Newton formulated them. So yes, it is certainly the rate of change of momentum. And for the purposes of non-relativistic mechanics, this is equivalent to m times d square x over dp square. But certainly, if I take relativity into account, I have to take the full equation, which is dp dt. That is a good point. Okay. So Maxwell's equations is something that you hopefully are very familiar with, given we spent quite a lot of time on it in the first half of the course. This is a set of 4 equations that tells you how the electric and magnetic fields evolve with respect to space and time. And you also are familiar with the notion of electromagnetic waves. Basically, if I consider these Maxwell's equations in vacuum, where rho equals 0 and j equal to 0, I can turn them into a wave equation for the electric and magnetic fields separately, and it turns out that they both travel at the same speed, which is the speed of light, c, which is 3 times 10 to the 8 meters per second, that you already know. Okay. So the laws of classical mechanics explain how objects move, how different masses move, and it concerns the subject of light or optics. Okay, so it explains very well, for example, all notions of physical optics and things like that. Again, I will belabor the point, the notion is deterministic. Okay, so once I tell you what the initial conditions are, I exactly know where the billiards ball is 15 seconds from now. Okay, so this is something that I will throw away in quantum mechanics. This will not be valid in quantum mechanics. That is exactly why I'm trying to say this again and again. And as is written in red, the classical paradigm was very, very successful in describing the physical world as we see it. Okay, it predicted electromagnetic waves that we measured in a lab. It gave us an understanding of the cosmos, and if you don't know this fact already, it led to the discovery of planets like Neptune. Okay, so unlike other planets which were discovered purely experimentally by observation, the presence of a new planet like Neptune was actually predicted by looking at gravitational perturbations and seeing that the trajectory of Uranus was slightly off, and this predicted the discovery of Neptune. So it's a very important and interesting piece of history that I encourage you to look at it. Also, ultimately, Newtonian ideas led to the construction of machines and ushered in the Industrial Revolution and things like that. As engineers, I'm sure you know a lot about it than I do. Okay. So given everything was hunky-dory, what's the problem? Why do we have to go beyond these laws of Newton and electrodynamics that was formulated by Maxwell? Of course, it is actually a very interesting fact in physics that at every stage of exploration, you find something new. What does that mean? So suppose if I simply look at this computer as an entire object without worrying about how it is functioning and things like that, it is a macroscopic object, and I can understand if I push it, it's going to behave like Newton's law. But if I zoom in and zoom in and zoom in on the computer and I see one tiny fraction of the computer at the atomistic level, then I find that I cannot explain many of the things that I can easily explain using Newton's mechanics. Okay, so this is a general prescription in physics in general, that as you change the energy at which you do the observation. So if you want to go probe an object at the minutest level, you have to bombard the object and you have to break up the object and find one particular atom and things like that. That usually takes more energy than just looking at the computer as a whole, right? So as you increase the energy scale at which you probe, you always find something new. So this is a general feature in physics. It's not a law by any means, but so far, whenever we have probed something at a deeper energy scale, we have found something new and interesting. So similarly, when during the turn of the last century, when people probed the atom, tried to understand what the atom is, new things started emerging. And you're all, I'm sure, familiar with Rutherford's famous experiment, the gold foil experiment. Before Rutherford did his experiment, I should mention that, the classical physicists had a picture of atom that was more like a jelly, right? So there is some positive ion, and then there is some negative ions all around in this jelly. They're all floating together in some weird way. This was a rough picture of what an atom meant to a classical physicist, but Rutherford actually tried to understand what this is in much more detail, and he did his famous gold foil experiment, and I'm sure you know this, so I'm not going to talk a lot about this. Basically what he did was, he took a thin foil of gold sheet, very, very thin foil of gold sheet, and bombarded it with some charged particles, right? So if there was ions all over and distributed equally, then these ions that you send in should be scattered by repulsion, right? So they should be scattered at all possible angles equally. But interestingly, that did not happen. So when he sent in this helium ions, alpha particles, he found that most of them passed right through the gold sheet and deposited right at the back of the ring. Okay, and a small fraction of them got deflected here and there and there. Some of them got deflected straight back, and some of them got deflected at the angle. By the way, this experiment is very easy to, or relatively easy to reciprocate in a modern lab these days. All you have to do is put one detector right at the back and one detector that is sort of moving, and you can just sweep through this detector and measure these alpha particles, right? And you can say, where do you find these alpha particles? Where is the concentration maximum? Where is the concentration minimum? All such questions. But of course, in Rutherford's day, technology was not so advanced. So it was actually a very laborious experiment where some people had to put some thin foils and try to see these helium ions hitting that and counting the flashes of light every time in a dark room. And it took hours and hours to take these readings. So it was actually a very difficult experiment to do in those days. Anyway, so this led to a very different, as you probably already know, this led to a very different view of what an atom is. Since most of the alpha particles just zip right through the gold foil, Rutherford and his collaborators postulated that most of atom is basically just empty. Okay, there is nothing there to deflect these guys, because if I put two like charges, they're going to repel and they're going to be deflected. If there is no deflection, there is nothing there. So obviously, most of the atom is just empty. But there is a small fraction that comes straight back. So he postulated there is some central core of positively charged ions that deflects everything right here. And everything that is deflected at a grazing angle right here and right here should be made up of some charges around the atom and distributed in some way. So the picture of atom that emerged, as you learned in high school, was that there is a positively charged heavy nucleus surrounded by negatively charged electrons. So this was okay. So this is all well and good. This doesn't gel with the classical picture of what an atom is. But how does it struggle with the classical laws of mechanics? We will understand that as we go along. The most important thing that immediately questions this picture and its compatibility with classical mechanics is the stability of atoms itself. If there are negatively charged electrons going around, they're not just sitting there, they're probably going around. And this picture is actually very convenient for a classical physicist because it pretty much looks like a planetary system, right? So you have a heavy sun with the planets moving around it. So a classical physicist in 1900 would have been very happy and very satisfied with this picture, because the atom is also exactly like that. You have some nucleus with electrons going around. But there is a problem with this picture, and the problem is that Maxwell's electrodynamics predicts that when charges accelerate, they radiate energy. Okay, this is not a subject that we have talked about in our first half on electrodynamics. It's actually quite an involved calculation, but it's a very interesting calculation how charges radiate. Basically, if an electron is accelerating with some energy, it's not going to just retain its energy, it's going to radiate its energy in electromagnetic waves, and it's going to lose energy as it keeps accelerating. Of course, if you have a heavy charged nucleus and electron, there is going to be acceleration of the electron, because you know this famous centripetal acceleration from a classical mechanics point of view. So the electron is going to accelerate, and Maxwell says when it accelerates, it's going to emit energy. And if it emits energy, it's going to lose energy. Finally, it's going to drop down into the nucleus, right? So this picture is going to be unstable because the electron drops into the nucleus. You cannot explain Rutherford's famous experiment. So the stability of the atom is under question if you simply apply the notions of Maxwell's electrodynamics and classical mechanics to this picture of atom, the structure of atom that Rutherford and his collaborators elucidated. So there is an incompatibility between these two ways of looking at things. So if the atom is this way with electrons surrounding the nucleus, electrons have to radiate energy, so they're going to fall inside the nucleus and everything is going to go haywire. And you can actually do a calculation and show that in 10 to the minus 24 seconds, the electron will rotate around the nucleus and fall into the nucleus and lose all its energy. Okay. So then there would have been no atoms, no molecules, no structure, and no me, no you, nothing. So that's actually a big problem. So the laws of classical mechanics and electrodynamics are not compatible with the structure of atom that emerged in the beginning of the 20th century. The other important aspect that emerged, that the very, in fact, even more central to the development of quantum mechanics than atom and the structure of atom, is what is called blackbody radiation. So what is a blackbody radiation? So it is common knowledge that when you heat something, it gives off some color, right? So when it gives off some color, it means that it is radiating some electromagnetic wave with that particular frequency, right? So when I heat a rod of iron, first it becomes some color, some orangish, and then it becomes reddish, and then finally when I heat it up so much, we call it white hot. We also say he's white hot with anger. So it's the maximum temperature that you can reach. So it becomes white hot. So thermal radiation, the study of thermal radiation, was actually of a lot of importance in classical mechanics. Okay. So what is thermal radiation and what is blackbody radiation? So thermal radiation is something that we are all familiar with and everyday experience. So sorry, before I proceed, Varun says why radiation was to be emitted means what explains electron should emit radiation. So the answer to this question is that when you can actually do a calc. So when we studied electrodynamics in the first half, we did not consider accelerating charges. Okay, so this is a completely different subject, and I cannot explain this in very straightforward fashion. You have to do a very long calculation, and you have to understand what are called Leonard-Weckert potentials and all those things. Not going into all these specifics, basically it means that when electrons accelerate, or a very charged particle accelerate, it has a radiate energy. Okay, it is not possible for any charged particle to accelerate and not radiate energy. If somebody is very interested in understanding why, I can actually reference the portions, for example, even in Griffiths. The later chapters in Griffiths also has a calculation. It's actually, I warn you, it's not a very easy calculation, but it is doable. So I can reference those chapters too. Why does atom have equal number of positive electric charges? Well, an atom is electrically neutral. So why it is electrically neutral? Why is a very difficult question to answer in physics in general, but it so happens that in all atoms are electrically neutral. So it means the only way it can be electrically neutral is if it has equal number of positive and negative charges. Somebody raised their hand. So if you raise your hand, please type your questions in the chat window and I will address them as we go along. Okay. Coming back to this, sorry. We already addressed. That was a relativistic question. So, okay. So again, whenever I heat up an object, it emits some radiation, right? Okay, no problem. I mean, it has nothing to do with what temperature. It doesn't have to be very hot, right? So even something at room temperature is still radiating something. The fact that you are not able to know that it is radiating is because the emitted waves are in a frequency that is not in the visible spectrum, right? So it's probably an object at room temperature is also radiating something in the infrared, for example. So you are not able to see things. It turns out that you have to actually heat up an object quite a bit for it to radiate in the visible spectrum. So the concept of radiation and absorption are closely related, right? So for example, if some object is in thermal equilibrium, it means that it absorbs, it radiates as much as it absorbs. Okay? So the concept of radiation and absorption are closely related to each other, particularly for bodies in thermal equilibrium. So it makes sense to study an object that is an ideal absorber. What does it mean? It's in some sense a theoretical construct, but you can actually make a black body very well in a laboratory. What you basically do is take a big box, probably put the inside with some black film or something, and put a very, very small hole, like this picture tells you, very, very small hole, and keep it in some temperature bath at some temperature T. And any incident radiation, for example, is going to be completely internally reflected, right? So maybe a small portion of it will come out and you can measure that small portion. That is what we typically do. But any internal radiation is going to be completely internally reflected and it's going to be absorbed very well, right? So once it is absorbed very well, of course, it's going to give out thermal radiation, and you can always measure this thermal radiation and find out the spectrum of this thermal radiation. A spectrum is basically what is the energy of the radiation that is coming out. What is the pretty much density, spectral density of the energy that is coming out. So, given an object that is hot, and if I measure the radiation that is coming out, so look at this graph, for example, I can ask the question, what is the amount of radiation between, let us say, 500 and 1000 nanometer wavelength, or which corresponds to some kind of energy, right? So then I can look at this graph and calculate what is the density, which is the amount of radiation between energy E and E plus DE. Okay, that is this graph. So this is called a spectrum of a black body. This is a spectrum of a particular black body, not any random object. This is spectrum of a black body. Okay, or cavity radiation, as it was also called. So again, Akash raised his hand. So please type your question in the chat window. I'll address it. The question is, in the turn of the century, the question was to so if there is total internal reflection, then how is there perfect absorption? Why aren't they just opposite of each other? I'm not sure I completely understand this question. Do you understand this question? So see, basically, if the radiation, suppose if you send in a beam of light and if it gets totally internally reflected and nothing comes out, basically it means that it is absorbed completely, right? So that is what I mean by perfect absorption in this case. Yeah, so, okay. So experimentally, you can do this observation and you can plot this spectral density spectrum of the black body as a function of energy or equivalently lambda. Energy and lambda, as you know, are inversely related. E equals hc over lambda. And this is what you get. Okay. And there is some curious features of this graph that was of very great interest to classical physicists. So initially, there was a huge increase, and then it attains a maximum. And then the spectrum drops as you increase in lambda, or rather decrease, go smaller and smaller in energy. Okay. The other factor is that if you see, each of these is plotted for a different temperature. So each of these is plotted for a different temperature, and as you can see, as I increase the temperature, the maximum of the spectral distribution goes to the left, okay, which means goes to higher and higher energies, or lower and lower wavelengths. Oh, so you probably have seen something called the Wien's displacement law that tells you that the maximum of lambda times temperature is a constant. So that explains why this inverse relation exists between the maximum of this lambda and temperature. But the other features of this particular graph are actually rather curious from the point of view of classical physics. It goes up and comes down. So the theoretical challenge in those days was to try and explain this using classical laws. If the rays are being, so there is a question, if the rays are being continuously reflected, then shouldn't they eventually exit out of the hole we made? No. So if there is more questions along these lines, I ask you to hold them. We can either push them to the discussion session, or I can answer them at the end. So since we are running out of time, I want to, if it is a perfect absorber, what is emitted on, what is being emitted? Radiation is being emitted. So the thermal radiation is being measured. All right. So there was a challenge in early classical physics to try and explain this particular graph theoretically. So basically, Rayleigh and Jeans were the initial people who tried to answer this particular question of trying to understand why this graph looks the way it does. And basically, they looked at the radiation inside the cavity, and if it is going to be internally reflected, then you can probably, it makes reasonable sense to approximate them as standing waves inside the cavity. And they said that, okay, if this cavity is of length L, this is an ideal picture. The final details of the calculation is independent of the exact structure of the black body. I can make the black body any structure, but the final formula that I show you would be valid. And the details of this calculation will probably be discussed maybe in a tutorial session or in private, not private, sorry, in another forum. So if this is a standing wave that is set up in some cavity, as you guys very well know, then the length of the cavity should permit some multiple of the wavelengths, right? Half wavelength, because they have to basically fix the wave inside this cavity. So this length should permit some number of half wavelength. For example, if this is one example in the picture where lambda is 12/5. So you can count the number of modes in a frequency range f and f plus df. Okay. So this calculation we will push to the tutorial session. I have not derived this calculation because my point is not to show how the calculation is derived, even though we will do it in a separate setting. Rayleigh and Jeans calculated, I think it was just Rayleigh calculated that the number of modes within a frequency interval df goes like the square of the frequency. Okay, 8 pi b f square over c cube, where v is the volume of the object. So it goes like f square over c cubed. Now, classical physics or classical thermodynamics, there is a beautiful law called the equipartition law. It says that if we have a total amount of some energy E distributed amongst a whole bunch of modes, then each mode, which is a thermal equilibrium with some temperature T, each mode carries with it an energy equal to K times T, where K is a universal constant called the Boltzmann constant. Okay. So each mode carries with it an energy KB times T. Okay. So if it's at some equilibrium at some energy in a thermal bath. So if this is the distribution of the number of, with respect to frequency, then the the energy distribution should follow this particular law. It goes like 8 pi v kBT f square over c cube. Okay, this basically means this equation, the second equation, simply follows from the first equation. So I can convert this equation that is in the frequency domain into an equation in the wavelength domain, because frequency and wavelength are related to each other through the energy. Somebody asks, will these slides will be shared with us? Yes, they will be shared with us. I'm also recording this. I think I'm recording this lecture. If it is successful, I'll also upload the recording. Let me see. Anyway, so basically, Rayleigh and Jean were able to calculate the spectrum of a black body, and this is their final formula. Forgetting, if you forget all the details of the calculation, don't worry, we will do it in a rigorous way. E of lambda d lambda basically goes like T over lambda to the fourth. Okay. Now, this equation is both right and wrong. So if I integrate this equation to allow all possible wavelengths at large frequencies, this equation diverges. So we can actually say it right from this particular equation. If f keeps on increasing, then each mode with some particular f has some energy. So I should keep on adding the energy of these modes, and if I add the total amount of energy, it's going to be infinite. It's going to be as large as possible. But the spectrum of the black body actually shows something very different. It shows that as I keep increasing the wavelength, it actually falls and doesn't actually increase. So why does it not keep increasing, and why does it just fall? So at large wavelengths, okay, this is called the ultraviolet catastrophe in classical physics in those days. At large wavelengths or large frequencies, people were not able to reproduce the spectrum that was experimentally observed with the classical laws of physics that they actually had. So there is some question. How can the interior region of a spherical body be a ground for the standing waves? There will probably be interferences between the different disks which follow different paths. This is actually a very interesting point about this, that the actual, so there is 2 points. The actual formula that was written down, which is the prediction of classical physics in this box here, is independent of the geometry. Okay, so quite frankly, I don't know how to prove it. So I don't know how, I don't know how to prove it. So Rayleigh, I think in his original calculation, did it for a cube probably. But no matter what, it can even be in irregular shape and this formula would still hold. Okay, so I don't know how to prove it. I can try to find out. If I'm able to find out, I'll share it with you. No, the interferences between different rays will not matter. Okay, in this case. So anyway, so if I only looked at the classical theory, at large frequencies it should diverge, as I told you, or equivalently at small wavelengths it should diverge. Okay, so as I keep increasing the frequency, the total amount of energy should go up, or as I keep decreasing the wavelength, the total amount of energy should go up. So I cannot have a curve that rises and falls like this. Okay, I should have a curve that just is very small at very large wavelengths, and at very small wavelengths or large energies, it just diverges. And that is actually a huge problem. So there was no way one could actually explain this blackbody thermal radiation spectrum using the laws of classical mechanics and electrodynamics. So simply by assuming that there is a certain number of standing waves and counting the number of modes and using equipartition of energy, saying that each mode carries an energy k times t, and counting the total amount of energy that is radiated, simply does not give you the right answer. It gives you the right answer for large wavelength. It doesn't give you the right answer for small wavelength. So that's actually curious. So that's why I said it's both right and wrong initially. It is right for large wavelengths, but something curious happens for small wavelengths, and classical mechanics is not able to explain this part. So along came Max Planck with his famous hypothesis of quanta. And he said the following. Okay, he said that yes, there is radiation inside the cavity, but you should think of this radiation not as just some standing waves, but imagine that there is a small, along this cavity, imagine that there is very, very small oscillators that can exchange energy with the cavity. Okay, imagine that this cavity and the periphery of the cavity is filled with some small oscillators that can exchange energy with the cavity. Now, this can be very confusing at the beginning, and if it is confusing to you, don't worry, it was also confusing to Planck, who gave this idea. He was not at all satisfied with this explanation. He regarded this hypothesis as a desperate attempt to understand this graph. Okay? Hello? Okay. So basically, and he also said another very important hypothesis was that the unit of energy that is exchanged cannot be continuous. Okay, classical physics tells you that there is no restriction on energy. You can exchange and you can absorb an energy that is any random value and emit an energy that is any random value. But Planck basically said that no, these oscillators don't exchange energy randomly. They don't exchange any energy. They only exchange energy with certain number of values. So based on this hypothesis, he modified this particular formula of Rayleigh engine into something that looks like this. Okay. Now the 8 pi v f square df over c cubed is exactly the same. If you forget the k times t, he did not take the equipartition of energy this way. 8 pi v f square over c cubed is still the same, but the kBt is now replaced by this particular factor. Okay. So basically, he said that this 8 pi v f square over c cube, this counting of the number of modes is still okay, but the energy, the average energy of the oscillator is not just kBt. kBt simply means it is continuous. Right? T can be anything, so the body can absorb or emit any amount of energy that it wants. But he basically said that it can only emit and absorb in certain quanta, and this means that its average energy is given by average energy of each oscillator is not just k times t, it is given by hf divided by e to the hf over kt minus 1. This is a rather weird looking formula. Okay. F is the frequency. Instead of writing nu, we wrote f. Nu is the more appropriate way of expressing frequency, but f is easier to write. That is all. But if you look at the this particular average energy of the oscillator in the energy regime where hf is much less than k times t. Okay, when kt is much larger than hf, this average energy of the oscillator is simply k times t. Okay, So K times T in some sense measures the amount of classicality in your calculation. So if KT is very large, then it is mostly explained by classical physics. But when KT is very small, when HF is very large compared to the K times T, then this formula is not valid anymore. The K times T formula is not valid anymore. So I have to replace this by HF over e to the HF over KT minus 1. So there's a question, how does this factor inform us that energy is quantized? This is a good question. So basically, there is two different things. When I say that an oscillator, so suppose if you have a simple harmonic oscillator, right, and you put it in a thermal bath, then classically I expect that the simple harmonic oscillator can absorb any amount of energy from the bath and emit any amount of energy from to the bath, right? There is no restriction on this. But if I say that it can only do so in certain discrete values, then the average energy would turn out to be this one. So to answer this question, let us actually move to the next slide. Again, this is not a complete derivation of Planck's formula. This is just to motivate you how the picture of quantization means that the average energy would be this one. So let us say that the oscillators can only exchange energy with radiation in quanta of h times frequency. Okay, h is some number at this point. So then Boltzmann statistics, which is a classical statistics, means that if you have an object with energy E in a temperature bath KT, then the probability of finding a mode with energy E would be E to the minus E over KT. Okay, so this is again a class. This is again a very well-established probability distribution. It simply says that if we have a whole bunch of particles with random energies in a thermal bath KT, the probability of picking a particle with energy E would be E to the minus E over KT. So then the probability of finding an oscillator, now these oscillators energies are quantized, so their energies can only be HF or 2HF or 3HF or 0 or 5HF or 6HF or things like that. So if I keep adding all these things to average energy, I should simply add all these energies and energy and divide by the total probability. If I do that, I get HF over e to the HF over KT minus 1. So the notion of the discreteness of the energy distribution, which tells me that the allowed energies are only this, leads me after a very simple calculation to this particular factor in Planck's formula. We will go through this in more detail during the Monday tutorial session that Vinod is going to conduct for you guys. So this is actually an interesting formula. So basically replacing this classical picture of any amount of radiation exchange is okay to only certain amount of radiation exchange is okay, basically explains this whole graph. So basically when KT is very, very large, this gives you the classical picture. When HF is very, very large, it gives you the quantum picture. Okay, so when you actually plot this, again, the limiting portions of this equation where HF is very large compared to KT and KT is very large compared to HF will be discussed in the Monday's tutorial session. It basically reproduces this beautiful blackbody spectrum that you see. So the blackbody spectrum is explained not by the classical Rayleighian distribution that is given by this, but by the quantum mechanical or so-called quantum hypothesis equation of Max Planck that is given by this. Of course, there is no way one can explain this quantization using classical mechanics. Okay, so one has to replace classical mechanics by some other theory. That is very clear. There is nothing in classical mechanics that tells you that energy can only be absorbed and emitted in discrete amounts. So this again gives you some kind of an indication that when you go to some energy regimes, it turns out that classical mechanics is not the right theory that explains everything. So one has to change the foundations of classical physics, and Bohr, as you know, I think most of you or many of you have studied the Bohr model of atoms in your high school. Bohr gave a very simple model of the hydrogen atom in atomic model, where he simply assumed the electron is going in some kind of an orbit, but with quantized energies, and he got the equation for the quantized energy, and the quantized energy is En is some basic energy times 1 over n square. So the quantization here comes from the factor of n square. Okay, n here is something called a quantum number. So energy of the electron in an atom is not any random number, but it can only be some fundamental energy times 1 over n square. It doesn't go like n, it doesn't go like n square, it goes like 1 over n square. Okay, which means as I keep going up and up in n, the energy of these electrons is smaller and smaller and smaller. Okay, so this is a very, of course, Bohr's model has been replaced by more sophisticated models using quantum mechanics. But Bohr's preliminary model tried to explain many of the curious facts about the hydrogen spectrum. I don't want to go in detail about the hydrogen spectrum, but basically the Balmer lines and the Lyman lines, he was able to explain the energy splitting. Basically, it is 1 over n1 square minus 1 over n2 square kind of a deal. Okay. One other thing that I forgot to tell you is the value of this constant called h. And the formula, the h is basically some constant that we do not know as of yet, but if you want to fit your theoretical curve with experimental curve, one has to choose h to be 6.6 times 10 to the minus 34 meter square kilogram per second. Okay, this is called the famous Planck's constant, and I think many of you have done the determination of Planck's, or you will do it when you do the physics lab next year. You will determine Planck's constant in a lab, so that's a very interesting experiment. So wait for one more semester, hopefully. When
you will also do Frankfurt experiment, and they will also look at this part.
You will also look at Frankfurt's experiment in the physics lab, PH102, and you will understand this a little more. So hopefully next semester, when everything is open again, and we'll see you guys back in campus. Anyway, so when one tries to build the quantum mechanical theory using these basic fundamental ideas, there is also other weird things that happen, and the most famous thing that people always talk about is uncertainty principle. The uncertainty principle tells you that you cannot measure the position and momentum of an object in the same direction with arbitrary precision. Okay, I can measure the position of the object in the y direction and the momentum in the x direction to arbitrary precision, but I cannot measure the position of the object in the y direction and the momentum of the object in the y direction to arbitrary precision. This is the uncertainty principle. We'll come to that in a second. But notice that this is in complete contradiction to Newton's second law, deterministic physics. Okay, Newton never said that there is a fundamental uncertainty in measuring objects. That is actually an experimental statement. It tells you that no matter how beautifully you design your experiment, there is a fundamental uncertainty you cannot escape. If we try to measure the position and object of position, momentum of the object simultaneously accurately, you won't be able to measure both of them with arbitrary precision. Okay, there is some amount of uncertainty that is involved. This is a fundamental feature of quantum mechanics, which cannot go away by just designing a very more refined experiment. This is a fundamental limit that nature imposes on you that you cannot possibly surpass, which is completely at odds with the classical understanding of what an electron is. For example, I can always measure how fast an electron is moving and where it is simultaneously accurate in classical mechanics, but quantum mechanics says no, you cannot. So there is a fundamental energy scale at which we expect quantum effects to show up, and that is called the de Broglie wavelength, which is given by h over p. Okay, so again, this is something that you have probably seen, and a nice exercise would be to try to estimate this wavelength for various values of day-to-day momenta, and you would see that for most day-to-day momenta, this h value being so small would make it extremely tiny, so it's very difficult to see. But for some values of p, which is pretty large, pretty small, then you will be able to understand what this h is, right? So if the electron is accelerated by voltage v, your lambda is given by p. So this is basically saying p is square root of 2 times m times e. So when you measure e in electron volts, you can estimate the wavelength lambda using this formula. So for 1000 volt, which is quite a large amount of voltage, your lambda is 10 to the minus 11 meters. There is some electron diffraction experiments that show this wave nature of electrons, but I will talk more about these diffraction experiments in tomorrow's lecture when I talk about the double slit experiment. So have this on standby. I will talk about this more in tomorrow's lecture. But basically, there is very strong experimental evidences in the early 20th century that told you that the fundamental physics is basically not classical but quantum mechanical. Okay, so what is the point of all these things? The physics of atoms cannot be explained using classical mechanics. There is at the fundamental level, the level of atoms and electrons and single particles, Newton's laws do not hold, things are not deterministic, which means we have to replace Newton's laws by something different. So we need a new paradigm to understand the fundamental mechanics of these particles, and this fundamental paradigm is called quantum mechanics, which is going to be our predominant occupation in the second half. It's radically different from classical mechanics. It is probabilistic, not deterministic. So we'll talk about how probability comes into the quantum mechanical picture starting tomorrow. And at very small length scales, at the atomic length scales, it is quantum mechanics that is a true description of nature. This doesn't mean that one should throw away the laws of classical mechanics. Classical mechanics still holds at everyday length scales. But when I try to talk about atoms and things like that, I cannot use Newton's laws anymore. We will be using this wave function a lot, and I'm sure you have seen the wave function before, psi. So starting tomorrow, I'll motivate what this psi means and why we need this psi. And this is called the probability amplitude. And tomorrow, my job will be to try and motivate what probability amplitude is. Why is quantum mechanics a probabilistic theory rather than a deterministic theory? And what does this probabilistic nature of quantum mechanics tell us? Okay, so tomorrow the lecture again would be to all of you together. Tomorrow will be the last lecture that is open to all of you simultaneously. Starting from next week, we will have discussion sessions with different subsections. Tomorrow, I will motivate this by using Feynman's famous thought experiment called the double slit experiment. Okay.